Hi everyone, my name is Jasper and this is work I did with my colleagues Chandra and Kong and my advisor Nadia at the University of Washington. I'll be talking with you about why making with digital fabrication machines can actually be incredibly frustrating and how we can help makers out by using the same computer-supported reasoning that lets programmers work quickly and accurately. Even as researchers and HCI have explored many new interactions and pipelines for fabrication, makers will always have to deal with difficult questions when working with machines. For example, consider three off-the-shelf 3D printers. Before a maker can start making anything, they need to decide how they're going to fabricate their design. Particularly in the case of larger prints, a natural question is, can this machine fit the model I want to print at all? Questions also arise after selecting a machine. Consider this open source pick-and-place machine which precisely places components onto a printed circuit board using several needles of different sizes. A maker experimenting with different placement orders will want to be sure that they are always using the correctly sized needle for a given component. If a maker doesn't already have personal experience answering these questions, the resources that can help them are quite scattered. These include material sheets, tips hidden in online forums, sites for looking up and debugging problems, hardware data sheets, and community wikis. However, it's an awful lot of work not only to find this information, but also to know how to even interpret it. It would be very helpful if we could distill some of this informal knowledge to a more accessible form. This leads us to ask, how can we formalize knowledge about when and how to use machines? To do this, we built Taxon, a language that encodes machines, workflows, and rules of thumb as programs. Taxon applies the safety and extensibility of programming to hands-on making. We implemented Taxon in a web interface where makers can browse a database of machines that are all represented programmatically as machine plans. These are loaded into the scene, which provides a simulation of the physical version of the machine. Here we've loaded a machine plan for a 3D printer. Then, makers write workflows which control the simulation. In this case, we're printing the first two layers of a cube. Finally, makers can browse and apply rules of thumb, which either filter the list of machines based on requirements or apply safety checks to workflow code. Now we can return to our original question, which is, which machines can fit my model? Now we could implement a special feature in our interface, but we actually don't want to stop there. There are thousands of decisions that an increasingly diverse base of makers makes with a plethora of machines, and we can never build an interface for all of them. Instead, Taxon's strength is that with its programmatic foundation, it lets makers write and share their own rules of thumb for selecting and using machines. Specifically, there are two kinds of rule of thumb. First, filtering rules of thumb narrow down the database of machines to show only machines that satisfy certain requirements, in our example, being able to print a model of a certain size. Second, action rules of thumb apply checks to the machine simulation as the maker is stepping through the workflow to ensure properties like picking up a PCB component with the correct needle in the case of our pick-and-place machine. So to check which printers can print a model of a given size, a maker goes to the list of rules of thumb and selects the one called work envelope is larger than, plus a value they enter. Here, a height of 100 millimeters. Enabling the rule narrows down the list of machines. Increasing the height to 200 millimeters narrows the list down to only 3 machines. Any filtering rule of thumb is a function that takes a machine and possibly a value entered by the maker through the UI. First, in this example, we parse the input for minimum width, height, and length of a model, for example, this low poly Pikachu. We compare the machine's work envelope dimensions to the minimum dimensions for the model and return true only if the work envelope dimensions exceed all minimums. The big idea here is that through code, we're able to take this knowledge about selecting a machine based on model dimensions and make it accessible to and extensible by all makers. So filtering 3D printers is just one simple example, but Taxon provides an infrastructure for representing all sorts of different machines and their rules of thumb. To learn more, please see our paper where we investigate several challenges in representing various experimental machines and workflows. Taxon applies the safety and extensibility of programming to hands-on making, and our next step is to move Taxon beyond simulation into physical settings. In the meantime, I'd like to thank my collaborators as well as the Alfred Sloan Foundation for generously funding this work. Thank you all for listening, and I'll be happy to take any questions.